All right, this is the introduction to Chapter 9, the source of the magnetic field. In Chapter 8, we talked about the magnetic field, the magnetic force, and its effect. We found a way to calculate the magnitude of that force, or the magnitude of the magnetic field, and we also found a way using the right-hand rule to find the direction. But we did not talk about where does this magnetic field come from in the first place. Well, that's what we're going to explore in this chapter, and in reality it all comes down to the fact that when charge are moving with respect to another object or from the point of view of an observer, it will create a magnetic field around itself. All right, now we're going to explore the Biot-Savart law, and this will help us generalize in the strength of the magnetic field and also in which direction the magnetic field should be pointing. All right, so let's dive in. So the first part is, let's just draw a current carrying wire. So I just said that the moving charge will create a magnetic field, and basically we're going to consider many charge that are moving in the form of a current inside a wire. All right, so first we have our wire. In this case, the current is pointing upward. We have a magnetic field circling around the wire. Now Biot-Savart tells us that we can find the magnitude of the magnetic field by applying this formula. So in the case of a current carrying wire, it is equal to, the magnitude is equal to the permeability of free space multiplied by the current divided by 2 pi multiplied by the radius or the distance from the wire. Now this term over here, the permeability of free space, is a new term. All right, so tell us how easily a magnetic field can travel through different object. In this case, we are only going to be considering free space. So this will always be U0 in this case. And it is equal to 4 pi multiplied by 10 power minus 7 Tesla multiplied by meter divided by ampere. All right, so this section tells us the magnitude of our magnetic field. Now we need to figure out in which direction this magnetic field is pointing. So we're going to use a modified version of the right-hand rule. What we're going to do is we're going to take our thumb and we're going to be pointing in the direction of the current. So let's take this wire, for example. The current is pointing up and the magnetic field will be pointing in the same direction as the curl of my finger. Now this part is a little bit confusing, because depending on where you are around the wire, the magnetic field will not be pointing in the same direction. The only thing that the right-hand rule tell you is in which direction. Is it turning counterclockwise or clockwise? Let's say we were looking at the top, it will be turning in that direction, which means it will be counterclockwise. Okay, so to see a better example, let's look at a second diagram that I have drawn. In this case, we have a current pointing into the board. So according to our right-hand rule, the thumb pointing in the board and the curl of our finger is pointing in the direction of the magnetic field. What this tells us is the magnetic field is turning around in the clockwise direction of our wire. Now, an important aspect here is depending on where you are with respect to the wire, the magnetic field will not be pointing in the same direction. Now recall that if we were to draw a straight line between the center of our wire, this is the radius of our wire, and the magnetic field, there will need to be a 90-degree angle between the two at all time. What that means is we know it's going clockwise, and we know that if we draw a line from the center to the point we are considering, they need to be a 90-degree angle. So in this case, the magnetic field will be pointing upward. If we consider the top part, again, 90 degree, the magnetic field will be pointing to the right, and so on and so forth for the other section. So you can imagine if you are at 40 degree, well, a 40 degree magnetic field will be pointing in that direction. All right, so that's important, and again, we'll practice this concept a lot. It's not obvious to grasp this concept at the beginning. Don't freak out, but we'll practice these. All right, so the second point that the Biot-Savart law tells us is that basically there's no magnetic field at the tip of our wire. So if we have a current, there is, in this case, if we were to use the right-hand rule, we have the current going to the right, our finger curling in, so we have the magnetic field going in that direction. At the end, though, the magnetic field would be 0. All right. Now, obviously, this law, the first conclusion, tell us that we can calculate the magnetic field when it is relatively in the center or close to the center with respect to the length of the wire, and we can find the magnitude using that formula. This other case is the other extreme at the tip is 0. Obviously, if we were to consider a point, let's say here, it's not near the center and it's not exactly at the end, the magnetic field will not be 0 here, but to calculate magnetic field at that point is a really complex calculation. We are not going to consider it in this course. So if you have to define the direction or magnitude of a magnetic field from a current carrying wire, this law will be good enough. I will never try to trick you in finding out what is the magnetic field here. However, you do need to know that you can use Biot-Savart law to find the magnitude, and the magnetic field at the tip is 0. All right. Last point, and this is regarding a current carrying loop. So it's a wire, but it's a wire in the shape of a partial circle. So in this case, we have a partial circle. There's a current going through it, and we want to consider the magnetic field at the center. So if we can imagine that if we were allowed to draw the complete circle, we want to know what is the magnetic field at the center. So first, let's tackle in which direction will this magnetic field be pointing. So same logic, we are pointing toward the current with our thumb. However, the thumb is changing. But if you notice, at all time, my finger are curling into the board, and you can imagine that if they were allowed to continue, they will come out of the board at point P. What that means is that all the charge that are moving here, from the point of view of the center, their magnetic field, the added magnetic field, is pointing out of the board. And again, we will practice this, okay? And we can using the Biot-Savart, so a modification to the Biot-Savart law, we can find the magnitude of the magnetic field, B, and actually this is the magnitude, so let's just write it that way. It is equal to the permeability of free space multiplied by the current, multiplied by the angle. I'm gonna mention what the angle is in a second. Divided by 4 pi, multiplied by the radius or the distance, the radius of curvature basically. So the distance from the center of the circle. This angle over here, and this is important, this angle is this one over here. There we go. So it's the circle of the it's the angle of the partial circle. Let's say if we were to have a complete circle, well, this angle will be 2 pi. Oh, it's the angle in radian also. That's a very important distinction. All right, so this is the first part of the introduction to chapter 9. We are going to cover some more theory in the next video, and after that we're going to be starting to solve some example to make sense of all of this. All right, see you in the next video.